All right. I only have one marker. Okay. Hello. How was the week? We said you have some fun? What do you learn about? Worksheets. What worksheets? What problems? Feature construction. Okay. We already covered functional approximation a little bit.
I mean, like tile coding in a sense, another type of function.
Okay.
Code is coding. Just going through it.
It's a different type of methods for. Okay. And how about algorithms for control with functional approximation? A little bit of that. What do you learn there? Sarsa and?
Like you just kind of show the whole roadmap of the Coursera course, like, and then discuss kind of like control type of algorithms.
Okay.
Just some pseudocode.
Pseudocode of all of these algorithms, or?
Well, yeah, I guess like they're just replacing like Q learning to stars, star, and then to expect stars. So it's just like one modification in the sense.
Okay. And what's the big takeaway from all of this? Was there something like some bigger lesson that he was trying to tell you?
Continuous task.
Hmm?
It's more generalizable. Continuous task. Compared to that. The sense that you can always parameterize everything in this kind of
Okay.
different kind of so on, and then do control those things.
Okay.
Like the mountain car example was what he tried to talk about a lot.
Okay. So what about the Monte Carlo example? What do you hear about?
How to formulate the problem.
Okay. Okay. Specifically mountain car? So what's the mountain car problem? Okay. So you just like have to push the gas really hard and then it goes up. Uh-huh. Okay. Why is that an interesting problem?
I think it was more if you're good at formulating a problem, you're good at reformulating. Or like you know the algorithm.
Okay.
Problem to math.
Yeah, I see. So realize how to formalize the problem and then how to apply the techniques to. Okay, that's good. All right. And with the Coursera, I think that there were some hitches, but everything is smoothed out now. Okay, good. All right. So today I said that, well, I guess this week, this is the only class, right? Friday is holiday. Happy holidays, everyone, for Friday and Monday. So we won't have classes on Friday and Monday. Oh, no, they took away the classes. Anyways, so we'll be back next Wednesday. And after that, that's the end. Okay. So I have one more class. So, okay. So that last class, maybe you can use it for reviewing some material and then just discussing stuff and maybe talk about the future of AI or whatnot. Bring your questions. And but today I said that I'm going to tell you some stories about functional approximation and control, because I think that this is a very interesting topic. And we talked a little bit about functional approximation in connection to just value function approximation when you have a policy that you're fixing and you want to approximate the value function of the policy. And there we were discussing what the options are and how would you use functional approximation. But in the case of control, it's a little bit different. In the case of control, what you're interested in is learning to control a system. That means finding a good policy, finding a good controller that achieves your goals. And the goals are formulated as, maximizing reward, total discounted sum of rewards in expectation, whatnot, right? As we usually do. And so Adam was telling you about a bunch of different algorithms. And you might be wondering about, okay, we have this zoo of algorithms. People keep coming up with different variations of these algorithms. And you have these parameters and those parameters. You can tune this, tune that. It's like, where is this going? Do we need a zoo of these algorithms, or is this is there an algorithm that is better than all of them, or like, what's the goal here? When would you be like, you discover a new algorithm, like, are you happy with it? Like, how do you even know that you're happy with it, right? So I thought that we should discuss this a little bit. And then I can tell you some stories about like what answers do we have to the questions that you can ask this way. So going back to algorithms, this is how we started the whole class. Then you're designing an algorithm, let's say for sorting. What is the thing that you're looking for? What algorithms are going to accept as an algorithm that is good at sorting? What are the crucial properties of these algorithms? So let's review this. So what is it? What is that we are looking for in an algorithm that is designed to solve sorting problems? Input is an array of numbers, and the output should be a sorted array of numbers. Someone tells you, hey, here is an algorithm for this. Are we happy with this algorithm? Are we not happy? What are the things that we are going to look at? Yeah? Time and memory complexity. Before that, there is another property that we shouldn't forget about. So that was good, but there's something really crucial. I can tell you an algorithm whose time complexity and memory complexity is awesome. It returns the array that was the input. Its time complexity is 01, takes no time, takes no memory, but it lacks some crucial property. What is that? It needs to be correct, yeah. So we need, okay, 3 things. Correctness or soundness. And then time and memory complexity under control as a size of the input, which in the case of sorting would be maybe just the number of elements in the array. Okay, so reinforcement learning. Oh my gosh. Control plus function approximation. We want to design algorithms for this problem. The criteria that we should be using to evaluate which algorithm is good or not good should be similar to the ones that we normally use, right? And those criteria have been proven by time that they're useful for selecting between algorithms, right? So then we have to decide about, okay, what do we mean by correctness? And what do we mean by time and memory complexity? I mean, memory complexity and time complexity is kind of self-evident, but maybe there are some differences here as well that we need to discuss, but we need to formulate the problem. So for the purpose of correctness, usually for algorithms in computer science, you have some input, and then you read the whole input, and then you produce an output. This kind of doesn't work for us, right? Because what we have is, well, okay, first of all, what should be the output that we need to produce? We have a number of choices. So one output could be just the optimal policy. But to describe the optimal policy, already this could be problematic, because describing the optimal policy would mean, or some near optimal policy would mean, to describe how to act at every state. And the point of functional approximation is that we want to have a way of doing all the computations that is independent of the number of states. So the memory and time complexity cannot depend on the number of states. That's the idea underlying functional approximation. So that frees you, functional approximation should be freeing you from dependence on the number of states. So if we ask, like, okay, what's the output of this algorithm? The answer cannot be, oh, just policy, because, like, okay, that's underdetermined. If you want a policy, in general, a policy would be, how to act at every state. That's maybe too much. Maybe it has to be described as a compressed form of a policy, but what do we mean by that? I don't know. Well, going back to functional approximation. So functional approximation, traditionally the way it is used, it's used to approximate value functions, right? It's used to approximate what type of value functions. Value functions of any policies or value function of the optimal policy. And we know that if you had Q star, for example, then acting greedy gives you the optimal policy. And we also know that if you have something close to Q star, acting greedy with respect to that is also going to give you a good policy. There is this continuity property there. So functional approximation can be used to approximate something like Q star or V star. How? So we do that by making an assumption that there exists some parameter vector such that for every state action pair, the optimal action value for the state action pair is equal to the inner product between some features with some known feature map. This is what you were talking about a lot, of how to construct feature maps. And the parameter vector, theta star. So this is known, and this is unknown. Okay. So when we set out to use functional approximation in RL, we are kind of thinking about something like this, right? That, okay, I wish I knew theta star. I wish the features were such that Q star can be expressed like this. And if I knew theta star, then I would know, I could return an optimal policy by just returning the parameter vector, because someone can write a little code that, given the parameter vector, can just return the greedy action with respect to the right-hand side here, right? So it's like You have your guess for theta, you plug that in, you take the inner product with the features. Maybe you have some other black box that returns the features given the state action pair. And then for every state action pair, you have a way of computing the policy. So in this case, you could say the goal is maybe just to come up with a parameter vector such that given a parameter vector, somehow someone can compute a good action. But you can generalize this whole goal by just saying that, OK, the way the whole computation should be happening is that, well, we have our imagine agent or learning algorithm. So this is the algorithm that we want to evaluate. It's going to interact with the MDP for a while, sending actions, and receiving next states and rewards. And this goes on for a while. And then at the end, it outputs something. It could be theta. It could be theta and a bunch of data, something. It just saves it. It's a package. And then that package can be read by some other algorithm, which is going to be given a state action pair. And its job is to output an action. So the inputs to this box, so this is the policy computation box, is a state action pair. Sorry, maybe a state, actually, right? Like, because it's a policy. It's like you're just given a state. And then you need to return an action of what action to take. And so we can agree that the setup should be such that the algorithm that we are talking about is going to output maybe something. It has to be some data that can be read by this other component. And it's part of the algorithm designer's job is to tell us what this component is going to be. A simple case could be just argmax with respect to theta transpose phi SA. So that's an example. All right, so with this, we can kind of say what correctness should mean. So correctness of the algorithm should mean is that you design nope. You design this box. You design this box. And these two boxes are designed in such a way that after the algorithm finishes, this algorithm first finishes, it has to stop at some point. It produces some data. And after this data is produced, that can be fed into this second box. And this second box is going to represent a policy. And this policy should be a good policy, right? Should be maybe epsilon optima. OK. So if this is the policy that's computed, maybe pi hat, then we want the value of this policy pi hat at every state to be as large as the optimal state up to some approximation error epsilon. So we'll allow some slack of epsilon. Maybe that's given to the algorithm ahead of time, right? And epsilon is going to be the input to the algorithm, because we are not going to be that strict that like you have to output the optimal policy. Maybe calculating the optimal policy without any errors is going to take too much time. We don't really need that. We just want a good approximation up to a fixed error. OK. So that's just correctness. So now we can also talk about the time and memory complexity. So both of these algorithms are using some amount of time, compute time, with interacting with this MDP, and also saving the data, so that uses up some memory. And yeah, thank you. And so that we are going to care about the time and memory complexity of the algorithm. All right, this clear? Okay. Ooh. So when we talk about these classical problems like sorting and like other algorithmic questions, then depending on the problem, we're happy if the algorithm's complexity scales polynomially in terms of the size of the input, or we really want to nail it, like in the case of sorting, we know that like the optimal complexity, optimal worst case complexity should be such and such in terms of the size of the input. In general, we care about just the polynomial complexity classes, because if something scales exponentially, then the empirical evidence is that you will find a lot of problems on which this algorithm will never finish. So the exponential complexity usually means bad news. Exponential function grows much faster than any polynomial. So we're looking for polynomial complexity in terms of both time and space. So that's the same here. So the target is poly time plus memory complexity. And well, of course, between the time and the memory complexity, if we are just talking about poly complexity, then time is the stringest, right? Like if you have an algorithm that has polynomial time complexity, it doesn't even have time to write down more than polynomial amount of data, right? Like if it keeps all the data that it ever calculated, it still uses polynomial amount of memory. So we care mostly about time complexity. We would only start to care about the memory complexity if somehow polynomial time complexity was not possible. Then as a second goal, we would say that, oh, at least give me an algorithm that has polynomial memory complexity. So let's focus on polynomial time complexity. So the question then is whether, for something like this, is it possible to have an algorithm that has polynomial time complexity? Classically, for sorting and whatnot, you have some obvious ways of measuring how big is the data. It's like number of bits used in the data, the total number of entries in the array, depending on the computational model. So what corresponds to that in our case? We are in this RL case. Well, we ruled out the number of states. So we don't want to see the number of states in the complexity results. We already had the results like that. That's really like that's a tabular case, right? So we discussed control in the tabular case, and we saw that polynomial time complexity was possible if you allow the polynomial to depend on the number of states. But here we are way more ambitious. We don't want the number of states to appear. What we are happy to see as replacing the number of states is the number of features. Okay? So the polynomial time complexity should be given as a function of the number of features. Usually I just use D to denote this, What else? Well, we have our precision, 1 over epsilon. That is also the number of actions. Sometimes you have something like the horizon. So the horizon for discounted problems could be 1 over 1 minus gamma. So we already, well, I don't know whether we discussed it, but like already if you are in the tabular case, this 1 over 1 minus gamma has to be there. Like a longer horizon problem, which is harder than a shorter horizon problem. It's not truly very much surprising, but you can get results that are polynomially scaling is the horizon, right? You don't want exponential blow up is the horizon. And maybe you have a, like if the algorithm is randomized, then this is a confidence parameter. And success means that you did return a policy pi hat, which is epsilon optimal. So success should be guaranteed with probability 1 minus that. If not with probability 1, then at least with probability 1 minus that. Okay. So you set that to 0.01, and then that means that with probability 0.99, the algorithm returns an epsilon optimal policy in the sense that we discussed before. And that's the goal. So now we have a problem which is properly formulated, and we can ask the question, okay, so let's say under assumption like this, that there exists, so the MDP and the features are given to you. The algorithm has to work for any pair of MDPs and features such that the action value function can be represented in the sense of that equation that's in the box over there on the board. Exactly. So for any such pair of MDP and features, the algorithm should succeed with probability 1 minus that and should be able to finish its calculation in polynomial time in all the relevant quantities. That's the question. Does there exist an algorithm that can do all of this? Okay. So let me write this down. Oh, this means exist. Okay, let's. So we fix the epsilon a h data. Such that for all M5 pair, M is an MDP. Pi is its features. Okay, this algorithm, I don't know. I call it A, but this is a different A than that. It's calligraphic A. You see this big leg there? It's like this algorithm A. So it's correct. So this algorithm is correct in the sense discussed above, and has poly the 1 over epsilon a h data time complexity. So one thing that was swept under the rug a little bit here is how the algorithm is given the features. The algorithm is given the MDP through these axes. And we discussed a few axis models the random access, the local access, and the online access. So random, local, online. So random access was that the algorithm is given a description of the state action pair and can ask for a transition at any state action pair. Yes. Global or random. I don't know. Yeah, like which one? Maybe I use global. Sometimes I use random because it's like random access memory. So random access or global access, and then local access means just that the algorithm is in this loop, but can go back and reset back to any state that it has seen before. And online access is that this reset is not available. So you can extend this to the features. So the features, you can have global access to the features. Same thing. For any state action pair, the algorithm can query the features of the state action pair. Local access is that for whatever state you are visiting, for every action, you can query the features. And same for online access. All right. So that's how you access the features in these algorithms. So now everything is well specified. And so there is this question, whether this exists. And now we can go back to our algorithms and then start to think about whether any of the algorithms that we have discussed would satisfy these properties, right? It's kind of like a minimum requirement that you want to have, right? Like here, I'm assuming that the features are really, really a good fit to the MDP because they can represent the optimal action value function. It's kind of a minimum requirement that I'm asking for. So sadly, so to break the tension, the answer is going to be no. Like no matter what algorithms were discussed in class, so the answer to the question, no. There is no algorithm that can do all this. Yeah. Yeah. It's proven. So that's a theorem. Let me call this a theorem. Yeah. Yeah, it is kind of sad. So it seems that, OK, this didn't seem to be very ambitious because we assume that the features are a very good fit to the MDP. We just asked the algorithm to figure out a few parameters. And we see that no algorithm will do it. None of Q-learning is going to do it, or SARSA, or expected SARSA, optimism you can add to it, anything you can think about, it's not going to cut it. All right. That's sad news. OK, so there are two ways we can go from here. So I can tell you a hint about why this is the case, or I can tell you better news. Who would want to hear better news? Really? OK, not so many. OK, actually, it's like 5. Who wants to hear about like what makes this theorem true? 2. OK. It's like a lot of people don't have any opinions. OK. I don't know. I can go both ways.
Sorry. Is this like as the number of samples also approach infinity, like in you're doing like some type of like Monte Carlo gradient method, then you're assuming n approaches infinity and you're talking about correctness, or are you fixing n before a priori number of samples you're taking?
So the algorithm is given an epsilon. That's the accuracy it's shooting for.
Okay. So as epsilon goes to 0, it should have n approaches.
As epsilon, yeah, like then we allow the number of samples or the time complexity to approach infinity. That's fine, because we allow a polynomial dependence on 1 over epsilon.
Oh, I see.
Right? Yeah. But actually, the counterexamples are such that even getting something, a ballpark, like even getting off the ground of like something not trivially bad. Like the examples are such that all the policies are really bad except for one policy, which is pretty good. And to get anything close to pretty good, like even halfway there or something, you're proven that the algorithms are going to require exponential amount of samples. Yeah.
It isn't like a polynomial algorithm, generalizable.
Yeah, I think that it depends on what you mean by nicely parallelizable. Because if you can cheat, I can cheat with that. Like it's really hard to formalize it in such a way that I can't cheat myself out of it and like call something nicely parallelized that just like not going to cut it in practice. Yeah. Yeah. So there are these speed up theorems actually. I don't remember any more of it, but when during my undergraduate, I learned about all these speed up theorems about how you can, in a cheating way, parallelize algorithms, and seemingly arbitrary speed ups are possible and stuff like that is true. So with good enough hardware, you should be able to do it. You will never have the good enough hardware anyways, but and then if you put those constraints in, then I don't think that there is a way out of this. Yeah. Quantum computers. Actually, the quantum computers can do I don't know, square root speed up at best, as far as we know. So it's not even magic. It's like it doesn't even move out of the polynomial class. It's like you had a D squared algorithm, and I know it's a D OD algorithm. It's like didn't do much. I mean, like, what's the box about that?
These all are NP hard problems.
I mean, this problem is exponentially hard, so it's even worse than NP hard. So there are some details here. So if I fix the number of actions to be very, very small, constant, just 2 actions, then the result what turns out to be true is that you have an exponential, the exponential lower bound on the time complexity is going to be true only under a complexity theoretic assumption, which is similar to P not equals NP. So in that case, but if I allow the number of actions to be already polynomial in the number of features and the horizon, so it's like, I don't know, d to the 1/4 and I don't know, square root h or something like that, the number of actions grows with those 2 other quantities like that, then you already have exponential sample complexity without any conditions. Yeah.
And also, are the approximation algorithms also like approximately hard in the sense?
This is an approximation result in a way because you have an epsilon approximation problem. And it's an additive approximation, but you can reformulate it as multiplicative and it remains the same. Yeah. It's like really devastating. Okay. Did I say that I use a lower bound? Yeah? Okay. Well, I don't know. Like, it just means that you prove that for any algorithm, the algorithm is going to require so and so much computation. Sorting problems. I think it's computing 101. You prove that any sorting algorithm is going to require n log n operations to sort arrays, right? Or even simpler problem. If you want to find in an array a particular number and the array was not sorted. Like you have to look at all the elements. It's kind of a needle in a haystack problem. So basically at the heart of all of these proofs is kind of like a needle in a haystack. And so you have these lower bounds, which are algorithm independent. So that's how we know that none of these algorithms are going to cut it. All right, so there are 2 ways to go. So one is to tell you like what makes these problems hard. And well, actually there is like a very simple grid problem, grid word problem. It's like 3 to the d states. It's like -1, 0, and +1 to the power of d. So that's like the grid. You can navigate on a grid. You want to get to one of the corners. You can formulate the problem like this. It's kind of hard. It's a variation of this problem. OK, so this is a minefield. So that problem is actually for the case when this assumption is replaced by the assumption that v star can be expressed with some features. If v star can be expressed with some features, plus you have access to the MDP, you can do the one-step look ahead. If you have a simulator access, you can get the optimal policy that way, or near optimal policy by knowing v star. So that's kind of a similar problem. And for that problem, if you just have this navigation problem on this grid that has 3 to the d states, and you can go to neighboring states, it's in a grid word, that problem has this structure already. You have to get to one of the corners, and you can set up the features in such a way that the cost to go to get to the corner is exactly, that's the optimal value function, the shortest path problem. And you can set up everything such that this assumption is met, it's deterministic, everything is deterministic. But if you don't know which corner to get to, how would you ever figure it out? There are 2 to the d corners. If you don't blindly bump into that corner, you will never, like, that kind of shows the basic logic behind all these proofs. So they're kind of like a needle in a haystack. It's like no algorithm will be able to do that unless the algorithm looked at pretty much all the corners. OK. So that's kind of the idea underneath it. There are subtleties here. So that problem is deterministic. There are only 2d plus 1 actions in it. So the number of actions is really low. And it's deterministic. And the rewards are deterministic. And if you have that, and you have this assumption that q star can be written as this inner product. So you have good features for q star, not for v star. That's polynomial. So that's a good news. So for deterministic problems, you have a positive result. So for q star, to make the problem hard, something needs to be stochastic. Because we know that if everything is deterministic, there is an algorithm that can do it. It uses basically optimism, and it's like a q-learning kind of thing. So OK, so that's a good news. So sometimes you can do it, but you have to further restrict things. So for example, this restriction of that the dynamics is deterministic and the rewards are deterministic are sufficient to get a positive result. So there are other ways of getting positive results. So let me just put this here. So for q star, we call this assumption is called q star realizability. And this was v star realizability. So it's another theorem that for q star realizability, just finite horizon problems, but maybe it works for other cases as well, and deterministic MDPs, the answer is yes. So the answer to that question. That's nice. But are we really happy with deterministic MDPs? Recall the discussion that we had at the beginning about, okay, stochastic, deterministic. It's like, I don't know. Like, it's kind of interesting. So there are other cases. So for example, if you have local access, and it's true that for every policy that's deterministic, the action value function of the policy can be written like realized with the features. Then the answer is again yes. It's a much stronger assumption. So now we are assuming that no matter how you choose a policy, I can just go and get some parameters such that the action value function of that policy can be expressed using the features. But I think that this is the assumption that most of the algorithms that are developed in RL for linear function approximation are assuming. And even those algorithms, like with epsilon gradient and whatnot, we talked about exploration problem. How important is that for the tabular case? It doesn't cease to be important just because we switch to function approximation. Of course, it's still important. And so you can't just rely on epsilon gradient. You have to do something else. But there are ways of going around that, and then you can get these optimal, these results. And they use optimism. All right, I think I'm going to stop here. Everyone should have a good holiday. If you want, you can drop in. I have office hours, and see you next week otherwise.